This is Alex. My Grantham ID number is G00035727, and this is my project for my ET450 Capstone. So what my project is an audio filter. Here's the schematic for it. The audio filter has 3 stages. We have a low-pass filter here, and as you can see, there's a 10 millifarad capacitor, which is extremely large, and then a variable inductor. Low frequencies will be shunted to ground depending on the adjustment of the potentiometer, and effectively all lows will be rolled off depending on the a variable inductor adjustment. And then this section here is the high pass filter, high pass to ground, so it's going to shunt high pass frequency ranges to ground, inevitably rolling them off in the frequency spectrum. Excuse me. This last section here is the split T filter or twin T filter, which provides 60 Hertz notch filtration. We have an op amp here which provides amplification because this filtration system will bring down our usable signal as well, and we need this amplification to bring it back up to where we wanted it. So the op amp brings everything else that we want back up to the normal level it was originally, except for the 60 Hertz peak, well, negative peak that this filters out. You'll see that we have 3 dip switches here which control the selection of the stage or branch of these arms, and it was not enough to connect and disconnect the input signal to the 3 branches, because if the outputs were all left connected to the output signal, then they would leach off the signal, and that wouldn't be good enough. So we have to change and isolate both the input and the output to the stages we want, and isolating the stages we don't want so that they don't leach off our signal. As you can see here, here's the breadboard. Sorry for the stability of the camera. These capacitors are all wired in parallel to give us the 10 millifarads capacitance, and I have a capacitance meter, so I was able to check all capacitance for the exact values I wanted, so tolerance here is negligible, including resistors. I bought the resistors in lots and kits, so I had enough to be able to test every resistor and choose exactly the ones that I wanted. The way that this system works is our input signal is coming here from the computer headphone jack. This is coming in mono, so I'm only using 1/2 of it. It goes to this terminal block here. The green one goes to the ground bus, which you see here on the breadboard, and the red goes to this alligator cable, which is going over to here and is connected to this yellow breadboard wire, which is the input of the circuit. The output is coming from this green breadboard wire to the yellow test cable, which is going here to this monster cable 1/8 inch phono extension. I say extension because, as you can see on the bottom, it's female to male. So this male right here is connected to the speaker system, which will provide the amplification we need to draw our measurements. And a few more things of note. You'll see that right here is the variable inductor for the stage, and then here, here, and here are the 3 blue pots we use to adjust, and then here is the 5 dip switch, here's a 3 dip switch, and here's another 3 right here. And you'll see that when I originally built this, I used the LTC6078, which I didn't know until it arrived, but it comes in an MSOP, this very, very tiny physical footprint or package here, which is very hard to deal with. So when they came in and I realized what I had received, I had to order these MSOP circuit board connectors. And actually, I mean, I ordered these and they were coming from China, so they came too late, and so I had to order some more anyway. So here you can see it makes it easier to solder and then connect your test cables. Well, I did that, but while I did that, the MSOP was introducing a short to my circuit for some reason. So as you can see here, it isn't an MSOP. The IC is not an MSOP into the circuit, but it is rather a LM, I think it's a, oh yeah, there it is, LM358 dip package. I have this, I bought 50 of them because that was the cheapest I could get. 50 was, this package of 50 was less expensive than buying one. And I also had an 8-pin dip socket, which you see here, which allowed me to solder the wires in place for testing before I had even inserted the IC, meaning that I didn't have to apply any heat to the IC at all, which is of course ideal. So what we're going to be, how we're going to be testing here is that I have a white noise 10-minute audio file that I'll pass through the system here, and it'll go through the circuit card. We're going to do it in bypass, and then apply the high pass filter and then the low pass filter, so that you can see on the spectrum analyzer here the difference, to see the difference in how it applies. So I'm using a decibel meter here, which will be for the 60 Hertz filtration, but for the white noise I'm going to use a spectrum analyzer application here. I'm going to raise my iPad up because, as you can see, that tiny little hole right there on the side at top edge is the microphone for the iPad, and I'm placing it here so that it's pointed directly at the woofer of the speaker. We have a few limitations here. So one limitation is the physical size of the microphone in my iPad, which is not very big, and the opening or the hole, sorry, I'm trying to adjust the screen here and it's not adjusting. There we go. Sorry about that. So we have the physical size of the microphone, which is very small, and this pinpoint hole opening, which you just saw, present a limitation to this low audio frequency spectrum. So our resolution at this low frequency range is not going to be very good at all. You can't see this very well, but this is 20 Hertz, this is 50 Hertz, this is 100 Hertz, so our 60 Hertz range is going to be right about here. But this is a free app, so I definitely don't have enough money to buy my own like Tektronix spectrum analyzer or something like that. So this is the best that I can work with. But if you look on the side, this is negative 40 dB, negative 20, 0, 20, 40. So each graticule represents 20 dB difference, which is pretty significant. So this is limited, but it's the best we can do. I'm going to use a spectrum analyzer for the high range, or the high pass filter demonstration, the low pass filter demonstration, but on the 60 Hertz notch filter, this isn't going to provide enough resolution. So what I'm going to do is use the dB meter that you saw beforehand, and we're going to use this 60 Hertz tone in bypass to test it and measure it in dB, then applying the 60 Hertz filter. Then I'm going to put it in bypass and use a 400 Hertz signal, and then put the 60 Hertz notch filter, apply it so that you see what it does, demonstrating that it resists, or not resists, but it attenuates the 60 Hertz test tone far more, like 100 times more than it will the 400 Hertz test tone, as it should, because it's a notch filter with narrow Q. One last thing that I'd like to mention is that with this MSOP that I stopped using, this MSOP requires actually a negative and a positive voltage in addition to ground, so I was having to use this dual power supply here, but as I moved to the LM358, which you see here, it only needs a positive power supply and ground. It doesn't need a negative rail to the breadboard power supply rails here. So what I'm actually going to be using are just two 9-volt batteries, which are connected in parallel here at the terminal block, which you can see here. Just two batteries, just to give it a little more capability if it draws current, which it shouldn't draw hardly any at all. So we're going to begin our test using white noise. It's pretty loud. Before we do that, I just want to give you a demonstration of the room quiet. So I'm going to stop talking for a second so that you can see the spectrum analyzer's measurements for the quiet room. Now this is still like, I have a lot of fans in this computer tower, about 7 or 8 of them, and I can't turn them off, so that's just the best I can do. So now I'm going to turn on the white noise. We're in bypass now. You can see because all the switches are set to 0. And this is our bypass measurement. So now I'm going to use my, I'm just going to pause it for a second. I'm going to use this table that I've created on the switch specifications. So first thing we're going to do is the low pass filter to ground. I'm going to turn on the white noise. And I'm going to change these switches to the low pass filter setting. So that's going to go to 1 and switch 2 is going to go to 1. Now let's look. You can see in the low pass range, right here, we have about 10 dB, about 10 to 20 dB attenuation in the low range. I'm going to put it back in bypass, adjusting my switches here. I'm going to give you one more look. This is white noise and bypass. And now we're going to go to the 400 microfarad high pass filter, which is switch setting 0100, and switch 2 is going to need to be 010, and switch 3 is going to be 001. So you see we have a little bit of a roll off in the highs. It's pretty minimal, but it is there. So I'm going to go back. Now we're going to do the 280 microfarad range, which is 0010. And switch 2 is 010. And switch 3 is 010. Okay? Again, we have a slight roll off in the high range here. And then our last one in the high pass filter is going to be 100 microfarads. And we have 00010. Let me change that right here. And switch 2 doesn't change. Switch 3 is 100 in binary. And again, slight roll off in the highs. Just to demonstrate this, I'm going to adjust everything for bypass again. So you can see it is a little bit higher. Now I'm going to turn this off. We're done with the white noise test. Now we're going to start with the 60 Hertz and switch over to our dB meter here. Close this ad and get the dB meter. Start recording. So that's pretty high. Before I do that, let me press pause here and show you what a quiet room sounds like. 41 for a quiet room. I'm going to turn on 60 Hertz. We have 102. Now I'm going to apply the 60 Hertz filter according to our table here, which is going to be 00001, and switch 2 001, and switch 3 doesn't matter at all. So as you can see, it's still playing. And it is still measuring about 20 above quiet room, but it's being filtered. Now I haven't touched anything, so the 60 Hertz filter is still on, and then I'm going to switch to the 400 Hertz, which is very loud. I'm going to turn it down to adjust it because it's maxed out the dB meter. I'm going to turn it down until I get like a normal rating. Okay, there's 108, 400 Hertz, and the 60 Hertz notch filter is active. So I'm going to put it back in bypass here. This is bypass. Close the add. So without the filter, in bypass mode, 400 Hertz is 102 dB. I'm going to turn it back on. So 60 Hertz notch filter 0001, which is right here, 0001, and then switch 2 is going to be 001, switch 2, 001, and as you can see, the 400 Hertz signal is still playing. Sorry, it's kind of hard to see. There we go. And it's coming through. So what I'm going to do is I'm going to switch it to the 60 Hertz signal, which is playing, but is being attenuated. So I'm going to turn the filter out. Oh yeah, sorry. I forgot to turn the amplitude back up. So I'm going to turn the amplitude up. This is bypass 105. So in bypass, zeros, zeros. Now I'm going to turn the notch filter back on for one last demonstration, which is 0001 and then 001. As you can see, close the ad. Stupid ads. The signal is still there, but it's much quieter. And as you can see, it's still playing here. There we go. Sorry, it's not the best. Here we go. You can see it's still playing. So now the 60 Hertz notch filter is on. I'm going to put it back in bypass 105. So there's the demonstration. Everything works as it should. Oh, one thing I should note is that I've learned through the testing is that this op amp here, which is used to amplify the signal back to normal, there really needs to be an op amp here and here in the low pass and the high pass filter so that we can introduce a more dramatic effect of the roll-offs of the lows and the highs and amplify the signal to bring it back. But I just learned this last week in testing, so I definitely don't have enough time to reintroduce two more additional op amps into my design. But there it is. It works exactly as it's supposed to. And again, I would have preferred more dramatic reaction in the high pass and low pass filters, but they're passive, so I guess I shouldn't be too surprised. And that is my project. So thank you.